CPU wants to talk to one of the peripherals, it actually talks to all of them at the same time. So the question is, why does this not conflict? I mean, how can you talk to one particular if all are listening in at the same time? And the solution, sorry, let's skip this. The solution is they have different addresses. So they see the address, and for example, if you have the cartridge, it sees its address 8000 something, then the cartridge knows, oh, this is not for me, I will not do anything. But if the cartridge sees address 6000 something, it knows, oh, I need to respond now. And the response types are very simple. So this is from the view of the CPU. The CPU wants to read something, then the peripheral needs to return something on the data bus. If it wants to write something, then the data on the data bus needs to be stored by the peripheral, whatever that means for the peripheral. Or, third case, it's not for the specific peripheral, it doesn't do anything. In particular, it must not write anything to the bus, otherwise you have a conflict. Now for the SDD, it also sits on the buses, on the bus, and it acts like a super peripheral in that it reacts to all the addresses except for the system, and it basically simulates all the peripherals that could be there that maybe aren't. So here you have the overview of what is simulated. So 2000, 8000, C1000, E1000, that's all RAM. So there you have the RAMs expansion. Then 4000, that's the DSR, which is for the operation of all things peripheral. This is also the area of the disk manager, and this also contains the RAMs register. The SAMS is basically a large array of RAM, but it gets mapped to the 4 addresses here, and it basically pages individual RAM regions into this accessible area here. And these registers are in 4000. 6000 is cartridge. 8000 is all sorts of system stuff. 8000 and 9000 is also included here. What the SDD can do is it can emulate the GROMs. So the GROM read and write is inside this area, so you can do a GROM emulation. Which means, together with Fixsound, you can basically emulate final GROM. In theory, I haven't done it, but it should be possible.
You could also emulate speech synthesizer there. You could also emulate speech synthesizer there.
Yes. If I knew how it worked, I could do that. From the hardware side, so this is bottom up, so you can't see much, but you basically have only 2 ICs on the board. On the left-hand side, you see a microcontroller, and on the right-hand side, this is just the RAM chip. The RAM is an SD RAM, as you would have found in a PC a long time ago. Now we have DD RAM, like double data RAM, 1, 2, 3, 4, 5. So this is kind of obsolete already, but it perfectly fits the purpose we have here. But it also means that 64 megabytes is probably the upper bound for that, because you won't find larger capacities. The microcontroller is so-called Cortex M. Now, Cortex is a class of microcontroller that was designed by ARM. If you look at the Raspberry Pi or lots of smartphones, you'll find Cortex A microprocessors or microcontrollers. A stands for application, is high performance. M stands for embedded and is kind of low performance. But low is also relative. It runs at up to 280 megahertz. This one is running at 180 megahertz. And there's also a Cortex R for real time, but we don't need real time. And for the M, you have 3, 4, and 7, and I'm using the 7 here, although a 4 would probably suffice. And again, the Cortex M is just a specification by ARM, and it's implemented by several hardware manufacturers. This one's by ST, so the actual processor is called the STM32, and then F7 for Cortex 7. Now let's dive deep a little bit. How does it work? But it's just 3 slides. Here you can see what happens on the bus during a read operation. You have a bunch of signals. Phi 3 is just the clock. It doesn't really matter, I just included it here. You can see that there are some wider and some narrower cycles. This is just rounding errors, because the logic analyzer has only discrete times when it looks at the signal, and then you get these rounding errors with small and narrow, with narrow and wide signals. Man enable always happens when something with the memory happens. This is also not important. You have the lowest address. These two are the important ones. This means the CPU wants to read something. Together with this, it means it wants to read the memory. But you can also infer this from the address. And this one means it wants to write something. And this is the highest address, and it's also not important. So a read cycle starts when this signal goes high. So we see this here. So this goes from low to high. This means the read starts. And again, it stops when it goes low again. Then, because of the multiplexer, you always read one word is a sequence of 2 bytes. So this is why you can see the address 0. First it reads the high byte or the odd byte, and then it goes down to read the even byte. So it's actually not the lower one first and then the higher one. This is one read cycle. And sometimes you also see, here we see a write, but only of 1 byte, which just precedes the read byte. Actually, if we write to say in memory, also multiplex, here we see the read is just one big read signal. But the write would have one hump here, then it would go high, and then we have a separate hump here. So it's slightly different between read and write. But what the SDD does, it basically checks the DB-in and the write enable signals, and checks if one of these signals change, and then it knows, oh, I have to react now. In software, as a high-level diagram, this looks like this. So at the top, we have these two. So the control is part of the bus, these 2 lines. They are connected to 2 pins on my controller chip. And whenever these signals go up or down respectively, these two, the controller will trigger an interrupt. And this interrupt will call the handler, either the read handler or the write handler. The handler looks at the address, and based on the address, it will decide which peripheral this is, and then delegate the simulation to the respective peripheral. Sometimes there might not be a write peripheral or a read peripheral, depending on the address range. Sorry, way around. In code, just to give you a feeling how this looks like, so it's C, like an Arduino basically. The yellow stuff is basically reading and writing these pins that the microcontroller has. So here you have a port B, GPIO, general pin input output B. So A, B, C, D, these are a collection of 16 pins. And I connected the address bus to port B from 0 to 12. And that's why I have to mask out the upper bits here, which are not relevant for the address. Then here, SDB, this is just a macro that also reads from a port. But just to simplify it a little bit, I gave this special names. So first we check if we're active. Active means that our crew bit has been set before. This is not shown here, but we only must react. So I should say this is the DSR read. So we're reading in address 4000 something. So we must check if we are active first, and then based on the address that's on the address bus, if there are special addresses that do something, but in the general case, we read our DSR code. This is assembly. We basically have an assembly code. We assemble it, and we basically get a binary. So we chop the binary into words and put the words in an array. And so we just access this array. We have to divide by 2 because this is an address for bytes, but we're accessing words. So divided by 2. So we get a data word. And then over here, we first put the upper, it's reversed. So this is the odd byte. We put this on address port A, which is the data lines. And then we say output this. Then we wait. Again, this is the address. This is the lowest address bit. So this is A0. In TI notation, this would be A15, but this is A0. So we have to wait until we reach the second byte. So first we have the first one, then it goes low, and then we have the second one. So we wait for this, then we output the second byte, and then we wait until the end of the cycle when DB in goes low again, and then we turn off the output back to input. Otherwise we would still send something onto the bus, which would crash the next operation. So I do this for every peripheral, for input and for output. And sometimes it looks much more complicated. Also, just one neat thing here, this is an address between 4000 and 5000 FFF. This X buffer R is an actual address. This is 4000 F100 FT0. And whenever this address is read, I'm not reading the DSR, but I'm reading an array here, the buffer. This is used to communicate data between the TI and the SDD. In assembly, this would like writing and reading from address 4000 F, also 5FF0, 5FF2, and so on. These are registers that are used to send data and other things back and forth.
You're using a lot of busy waiting.
Yes.
That's the easiest way, of course.
Yes.
Is there no way for event-based programming?
There's no use because whenever, so I do this for the interrupts whenever something happens, but once I have a read signal, nothing else will happen during the time. So busy waiting is perfectly fine.
Okay.
The big question is, of course, is this fast enough? If I would do this with an Arduino, this would not be fast enough. but we're running with 100 megahertz, so is this fast enough? If you look into the spec, so here's a snippet from the spec. You can see, you could also see it from my screenshot of the logic analyzer 2 slides before. But here the read cycle begins. This is the change from odd byte to even byte, and here the read cycle ends. This entire cycle is 2 microseconds. That's just a specification. So that means per byte we have 1 microsecond. Sorry, this should be a micro, not really micro. Now each cycle, so this part here has several phases. Here the address or the data or both is put on the bus. But to stabilize we have to wait a little bit. Then this last one here, the green period, is where the data is actually read. So that means between these plus, so the yellow area here is the time where we can do something. So if this is a read, here we have to wait until the address is stable, then here we do something, and in this period we must provide the byte. And this yellow area is 3/4 of the half of this, so it's 740 nanoseconds. If the speed of the controller is 180 megahertz, this means we have 5.6 nanoseconds per cycle. So if we divide these two, then we have 134 cycles per byte that we can use. And that's quite a lot, relatively speaking. So you can do quite a lot, but you have to be careful. There's a lot of internals in the microcontroller that you have to take care of, but I won't go into that. But the message is, it is possible. It's fast enough, yes. Now, since it's very similar to TIPI, which is already available, here I have a small comparison with it. It's similar, but it has a quite different architecture. So I already talked about the microcontroller used. I'm using an M, and he's using, or TIPI uses an A on a system on a chip. The biggest difference is I'm using what's called bare metal. That means I have the chip, the microcontroller, and I program the microcontroller. It's executing the microcontroller assembly. TIPI, on the other hand, also has this microcontroller, but on the microcontroller runs Linux, or more precisely, the Linux kernel. And they're using Python that runs on Linux, which uses the Linux kernel on the controller. That means, even though the controller is much faster, their execution is much slower, because they have several layers on top of each other. That means I have 180 megahertz, they have a much higher frequency, but it has to be divided by a factor I don't know. So it's hard to compare. But it also means, so I have this SDRAM on my board. The Raspberry also has RAM on the board. But because they're not using the controller natively, but have these layers and layers on top, the RAM is mostly inaccessible, as far as I know. I don't have a TP, but I would be surprised if they could actually make use of the RAM they have.
I think it even depends on having the 32K expansion hardware before the TP. So it's separate.
Yes. No, what I'm saying is
I know the
Raspberry-
internal RAM of this
yeah, the
Pi.
Raspberry I think has 1 gigabyte or half a gigabyte of RAM,
Yeah.
but the TI cannot use this
Mm.
because there's no direct access from the GPIO bus to the RAM, and whatever they wrote as a DSR is too slow to serve the cycle requests by the CPU fast enough. Finally, the peripherals, they're basically limited by what the MCU provides. On the TP, it's limited by the board, what the Raspberry Pi offers. And finally, I use a custom board, and they use an off-the-shelf board with a custom adapter. That basically, yeah, that's the status what I plan to do. Right now, the prototype works with TI Basic. Extended Basic uses slightly different subroutines for parsing whatever you type. So I probably need to do some modifications there for the Extended Basic, and I need a PCB for the extension box. Yeah, and I need to do some testing. But this basically concludes my talk. I probably ran over a bit, but if we are short on time, we can drop the second talk of mine. But I wanted to give you a thorough introduction of this. Thank you.